My name is Vishal Anand, 19ME10080. This is my submission for seminar under the course AI60002 Machine Learning for Earth Science System. Professor Advait Mitra. My topic is Deep Learning in Turbulence Modeling. Why this odd topic? I took this topic because I wanted to explore how MLDL can be combined with fluid mechanics. Since fluid mechanics is physics based and MLDL is data based, there are very less research in this field, and due to my interest in both the topics, I choose to explore this section. In this seminar, we won't discuss only one paper, but we will discuss multiple papers and will try to understand the application of MLDL in turbulence modeling or fluid mechanics. So first of all, let's understand what is turbulence. In simple language, turbulence is unsteady flow of fluid. Here in the picture, we can see the turbulence formed at the trailing edge, this part. I can zoom it, but it's not happening. This part is the turbulence that happening at the trailing edge. This one is taken from my research work that I had performed. These numerical simulations take lakhs of seconds to give the results that are similar to how it is going to behave in the real world. Computers have become so advanced that we are able to process it. So this one is the first paper, Turbulence Modeling in the Age of Data by Karthik, Lacrino and Heng. So they discuss about Rand's equation, basically how modeling is done in the age of data. So earlier simple engineering models were calibrated using data. But now from last 4 to 5 years, with the availability of large and diverse data sets, researchers have begun to explore methods to systematically inform turbulence models with the data, with the goal of quantifying and reducing model uncertainty. Now you can break turbulence modeling into two types, two major couple of groups. There is RANS, Reynolds Averaged Navier-Stokes, which kind of try to model average flow quantities such as mean lift or mean drag. And another one is LES, Large Eddy Simulations, where you try to model unsteady or moving flows. So let's first of all understand what is RANS. RANS is a numerical method to model a turbulent flow where the flow quantities are decomposed into their time average and fluctuating component. Here the model is the velocity in the average and that the fluctuating component, where the averaging of Navier-Stokes equations is a non-linear Reynolds stress term that requires additional modeling to fully resolve the system. This is the non-linear stress, Reynolds stress, that is happening. These Reynolds stress depend on small turbulent scales that we do not want to resolve, and so we are going to approximate these into terms of the large bulk variables that we do not want to model and measure. So that's the closure program for RANS. The paper Reynolds Averaged Turbulence Modeling using Deep Neural Networks in Embedded Variance by Julia King, Andrew and Jeremy solves RANS closure turbulence modeling. So let me go back to the RANS equations. Here there are a lot of approximations, these Reynolds stresses, lot of approximations in the flow of, in terms of bulk quantity, in the flow of the eddy viscosity model. There are Prandtl mixing length model hypothesis, K epsilon models, omega models, split models, and all of them have known deficiencies for certain classes of separated flow. So this paper uses neural networks to better the models for how those Reynolds scales behave for large scale mean flows. Now come to large eddy simulation. Similarly, closure problem for large eddy simulation is that we have some high Reynolds numbers at very complicated turbulent flow. What we will do is we will simulate it in coarser grid. Here we can see that the picture is highly quality. Here we defined it in coarser grids. So we will be saving time, expense and time to simulate. We are going to simulate unsteady time evolving Navier-Stokes equations on these coarser grid by low pass filtering the equations here, and we will try to understand what happens in this kind of very very small, very small boxes, these small boxes, and how we are going to model how these affect the physics. This type of modeling is called subgrid scale modeling, where we observe every single coarse grid and how the turbulent fluctuation is affecting large scale Eddy or Stokes equations. The paper Subgrid Modeling for Two-Dimensional Turbulence Using Neural Network by Maulik, San, Rashid and Vedula are using deep neural networks to model what the subgrid scale physics, how that's impacting this kind of large scale Navier-Stokes equations. So they have built a custom neural network where they are putting in these quantities of interest as an input, and they have designed a neural architecture, deep learning architecture, and there this is what comes out as an output. By this they get very large, nice Eddy simulation models that are closed to not by these kind of heuristics, by hand physics closure models, but by kind of a learned deep learning closure model. So they trained it on high fidelity direct numerical simulations where they know the truth, and in principle they can learn better closure models for how the subgrid physics affect the large scales. We talked about deep learning for turbulence modeling. Now look at this, machine learning for fluid mechanics by Steve L. Brunton, Brent Knack and Petro Kumaskas. We can say both are same, but at the same time they are not. Field of fluid mechanics is rapidly advancing, driven by a lot of data that we generate from the experiments, field measurements, large scale simulations at multiple spatio-temporal scales. So, and this drives a lot of data, and this offers techniques, ML offers techniques to extract informations from data which can be translated into knowledge. So this paper discusses about emerging opportunities of ML for fluid mechanics. We have a very long way to go, use machine learning or deep learning for understanding ever-changing physics. Fluid dynamics presents challenges that have lots of challenges in the fluid dynamics using machine learning that differs from those tackled in many applications such as image recognition and advertising. In fluid flow, it is often important to precisely quantifying the underlying physical mechanics in order to analyze them. We can see the fluid flows exhibit complex multi-scale phenomena, the understanding and the control which remain largely unresolved. Experiments may be difficult to repeat or automate, and various simulations may require large-scale supercomputers operating for extended periods of time. Because of many fluid subsystems are non-stationary, and even for stationary flows, it may be prohibitively expensive to obtain statistically converged results. Fluid dynamics is central to transportation, health and defense system, and it is therefore essential that ML solutions are interpretable, explainable and generalizable. I suggest that this non-exhaustible list of challenges need not to be barrier. To the contrary, it should provide a strong motivation for the development of more effective ML techniques. These techniques will likely impact several disciplines if they are able to solve fluid mechanics problems. This presentation or seminar is referred from the four papers. That one is the turbulence modeling in the age of data, second Reynolds Averaged turbulence modeling into deep neural networks with the embedded invariance, subgrid modeling for two-dimensional turbulence using neural networks, and machine learning for fluid mechanics. These papers you can read it. These are the very good papers, and one of the few papers who have ML or DL for fluid mechanics. So this is my submission. Thank you.